Hello, welcome to lecture 28. We're going to be talking about the strong form of mathematical induction today, and that'll be the end of chapter 5. So the next topic coming up, section 6.1, is an introduction to relations. So yeah, let's see what's the plan for today. That looks pretty easy. There's just going to be a little bit of introductory stuff, and then we'll go through some examples. So let's hit it. So first of all, there's a confusion of names of what's often called PCI, principle of complete induction. Uh, it goes by a lot of names, though. Let's see, strong induction being one of them, but complete induction, and sometimes this is a little bit old school, but sometimes people will say a course of values induction. So there's what it looks like. For all k, P0 and P1 and P2 and blah, 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 up to Pk minus 1 are true. That's k statements are true from 0 through k minus 1. And the truth of all of those needs to imply the kth one. So it's not like saying the previous domino knocked me over. It's like saying all the previous dominoes came on and piled on and knocked me over. That's what happens to Pk. These abbreviations are fairly standard. Principle of mathematical induction is what we've done previously. That's ordinary induction. And PCI for the principle of complete induction. They're the same. But from a logical standpoint, they actually are equivalent. It's a little bit tricky to prove that they're equivalent, but really not even that bad. So why? Well, there's times when complete induction is just more convenient. See, here's what happens when you're doing complete induction. You get to assume that everything prior was true, and then that's what sort of your ammunition in trying to prove that Pn is true. So that's a lot more stuff, and so that's really why it's sometimes called strong induction. You've got a lot more going for you in terms of hypotheses. It's much stronger to say that all k minus 1 statements, or all the previous statements anyway, are true. Not just the previous one, but all the previous ones. So here's the outline. It's fairly evident, I suppose. The one thing that's problematic for me personally, I have never totally wrapped my head around this, but here's the issue. Technically, a complete induction proof doesn't require a basis. And yet I've run into so many instances where if you tried to prove it without stating the basis, your proof really didn't hold water. So just as a pragmatic matter, I suggest you investigate the basis statements, and often several of them. So write down a basis, even though purists will tell you a complete induction proof doesn't require one. But in the inductive step, well, we're doing what I just talked about. You have the conjunction from 0 to k minus 1 of pi. All of those statements ANDed together implies pk. And so that's what you need to verify in the inductive step. So let me try to bring some light to this issue about basis or not. Think about what happens when you're at the n equals 0 stage in a complete induction proof. The inductive step looks like this. You have the AND of a whole bunch of statements implying P0, but there aren't any statements prior to P0. So that conjunction of an is actually empty. There's no statements ANDed together at all. And that's what's supposed to imply P0. So you have to think about what does it mean to be a conjunction with no terms in it, no statements involved. And like we saw when we looked at an empty sum, and it turns out it behaved as if it were the additive identity, or an empty product, and it behaved like it was the multiplicative identity. Well, an empty conjunction should behave like the identity for conjunctions. And the identity for conjunctions is a tautology. That's it was actually called the identity law when we were studying logic. So if you're correctly getting the inductive step done in a strong induction argument, you're going to be you're intentionally going to be dealing with the case where P0 is implied by a tautology. So if you have a tautology implies P0, what is that? Well, actually, it's P0, right? Tautology implies a statement has exactly the same truth values as that statement on the right-hand side of the implication arrow. So that part is why you're proving the base case, or why it's sort of unnecessary to prove the base case. If you do the inductive step correctly, you will have handled this. The problem is it's really easy to overlook that whether you've handled that or not, and that's why my recommendation is just do the base case separately anyway. I think that a majority of the complete induction proofs that I've seen in publications have a base case written down, even though the argument just above tells you that in fact it's not necessary. But yeah, let's push on. So I wanted to say a few words about this idea that the ordinary induction and complete or strong induction are equivalent. Think about this, what it says on that first bullet. If a statement can be proved by ordinary induction, then you can certainly prove it by strong induction. Why so? Well, strong induction means you get to assume everybody prior from P0 up to Pn minus 1 in trying to prove statement Pn. And ordinary induction, you'd only get P sub n minus 1. But that's fine. If you know all of those statements are true, then certainly it's true that Pn minus 1 is true. So yeah, it's just a particular one of those 0 through n minus 1 things that you need. So you know that one's true, and then you just do whatever the ordinary induction argument said. So if you have an ordinary induction argument and you're trying to do it by strong induction, it'll be okay. But what about vice versa? Suppose you have something that can be proved by complete induction. Can you show that you could also do it by ordinary induction? And there's a kind of a standard trick here. You create a whole new family of statements that are related to the P's. And what they are really, you change the statement from P being the kth domino fell, P sub k would be the kth domino fell, to P case it would be everybody from 1 through k has fallen. So in practice, this looks something like this. Q sub k is going to be a whole collection of PIs being true. For all I in 0 through k, PI is true. So then, how is that going to help? Well, if you're doing the stage where Q sub k minus 1 implies Q sub k, that's an ordinary induction, the previous stage implying the current stage. But because of the way this Q was defined, you're really doing the same thing as all of the guys from 1 through k minus 1, implying the kth one. So it's really the same thing as a strong induction argument, but this Q family, you can just prove that your statements with ordinary induction. So the details in that are slightly interesting, slightly technical. I didn't want to get too deep into it, but I just wanted to sketch for you the idea that complete induction and strong induction are really, equivalent in terms of what they can prove. All right, so that's probably enough babbling about, what's going on. What as an introduction, let's actually do some examples. So the first one we're going to do is the fundamental theorem of arithmetic, and I don't know if it has become clear to you so far in your studies, but you've run into things called fundamental theorems a couple of times, at least 3 times that I can think of. And you are going to run into more things called fundamental theorems. People tend to, as they're refining a particular area of math, kind of organize and get the structure down very, very accurately with in terms of dependencies, what statements depend on others. So a fundamental theorem is one that proves many other things. So which ones have you seen so far? That's the fundamental theorem of calculus. That's the one that says, you can evaluate an integral across some interval by just looking at an antiderivative at the endpoints, and you do that little subtraction thing, f of b minus f of a. But why is that fundamental? That fundamentally what that does is link the two areas, differential calculus and integral calculus, together. Um, the fundamental theorem of algebra. It's really polynomial algebra. Every polynomial factors, right? And you can factor it into linear, but sometimes also irreducible quadratic terms. If you go to the complex numbers, then you can factor everything completely, and that's a nice feature of the complex numbers. But this is the statement, how it works when you're just talking about real coefficients, and so the factors would have to have real coefficients as well. So if you're strictly working in the realm of the real numbers, you get linear and irreducible quadratic terms. If you expand to the complex numbers, then you'll still get linear things, but that's because you're in the complex numbers. These formerly irreducible quadratics reduce, and so that you get a factorization into things that look like x minus one complex number and x plus that same complex number, what are known as complex conjugates. So, well, that's an extension of the fundamental theorem. But here's the fundamental theorem of algebra for just ordinary real polynomials. The fundamental theorem of arithmetic, that's one we actually want to talk about, is actually a pretty simple statement. It's just saying that there's a unique prime power representation of every positive integer. You can uniquely write a thing as a product of primes to various powers. There's a slight issue with uniqueness. Of course, you could fiddle around with the order of those factors, and that would have no effect. But up to ordering, unique. So, well, here's a fairly obvious statement. The prime factorization of a number and the number right before it almost have nothing to do with one another. In fact, one of the things that they do have to do with one another is that they have nothing to do with one another. If a particular prime divides k, it's certainly not going to divide k minus 1. They differ by 1. If one of them is 0 mod p, the other one is not going to be 0 mod p, even if p is 2, even the smallest case possible. So numbers that are 1 apart just are not going to have any primes common between their factorizations. I guess that's something, but it's a little bit hard to use in an argument. So what we're going to need to use to do in an argument is refer to other numbers smaller than it, not just the previous one, certainly not the previous one. What actually, the nice way to prove this thing is to do a little lemma first, which is to say that every number has at least one prime factor. And so that's it. For every natural number, if n is bigger than 1, because if n is 1, it's not going to work. And if n is 0, I don't even know what we do there. But if it's bigger than 1, it has a prime factor. That's the lemma we'd like to prove, and we're going to prove that using strong induction. So I didn't do the thing where I reveal this proof a little step at a time. It's just plop out there in front of you. So maybe I can highlight things as we go. Again, you start off by saying proof, just to indicate what you're doing is lapsing into a very formal style of argumentation. Let them know up front that you're using strong induction now, not just regular induction. So what are we going to do? Well, we'll consider an arbitrary natural number n greater than 1. And it's often smart to start off with a consider sentence. Or you could do it as a suppose. Suppose n is an arbitrary natural number with n greater than 1. Anyway, if n is prime, then it clearly has a prime factor. No, it's its own prime factor. So suppose that n is not prime. Well, that means it's composite. That's the alternatives for. There's one other alternative, prime, composite, and units. The units in the integers are just 1 and minus 1. And we're cool because we're in the case where n is bigger than 1. So the only alternative to prime is composite in our setting. So what's it mean? Well, a composite number is one that can be factored. So we know n looks like that. N is a times b. Or some pair of numbers, a and b. And, I do know that these numbers are bigger than 1, don't I? Part of the definition. So since a and b are factors of n and both are greater than 1, it follows that, well, we're just looking at a. A is less than n, and it's bigger than 1. It's also true that b is in that range, but you don't even need that. You just pick one of them and go, all right, it satisfies the inductive hypothesis, doesn't it? It's a number, saying that this guy has a prime factor is one of the many statements between 0 and n minus 1. So the inductive hypothesis is now applied, and that means that a has a prime factor. Let's call it p. All right, so that means p is a divisor of a, and we already know a is a divisor of n, so by the transitive property of divisibility, p divides n, and that means n has a prime factor, QED. So we've just done the part that shows that n has a prime factor. Let me just talk to you, I didn't make a slide about this, but it's probably a good exercise to try to now, with this lemma in your toolkit, try to prove the actual fundamental theorem using complete induction. What are you going to do? You're basically going to say, take an arbitrary number. I know it's got a prime factor, so I can divide that out or factor that out of its factorization. I can take n and divide it by p, and I will have an integer again because that p divided evenly into n. But now I've got a smaller natural number. And what's the inductive hypothesis tell us? If we're trying to do the full proof of the uniqueness of the representation, it tells us there's a unique representation of n divided by p in terms of powers of primes. Now it's just a matter of incorporating p back into that to get a unique representation for n itself. Not a deep proof, not really all that hard, but it's probably a good one to use as an exercise to see whether you can write one of these things up as a, in a facile way so that it looks nice when you're done. Another area where you'll see proofs using complete induction generally is what are known as recurrences. So this is when some number doesn't have a formula for it per se, but it has a way of computing that if you've done all the numbers up to a certain point, you can get the next ones. So previous values give you the next value. And I think most people have heard of the Fibonacci numbers. They're defined recursively by this rule. The nth one is the sum of the one before that and the one before that. There's 1, 2 back. There's lots and lots of sequences that are defined recursively like that. I probably was supposed to say something else here, that there's also a starting point for the recursion. Because if you want to know what f0 is, well, fn minus 1 and fn minus 2, those wouldn't be natural number indices. So that's they might not even be defined. So usually you pick in the case of the Fibonacci numbers, people usually use either 0 and 1 or 1 and 1. Those give you the same sequence, just shifted slightly, so it kind of doesn't matter. But yeah, so usually you have initial values and then the recurrence takes over and will generate everything from there on. So anyway, what's our current interest in such things, sequences like that? Well, if you try to prove something about a recursively defined sequence, it's going to be very nice if you know something is that whatever the something you're trying to prove is true for the earlier values used in the recurrence. So I might have a statement about the Fibonacci numbers. I'm trying to say that thing's true. It'd be cool if I knew that it was true at the 2 previous stages, because then I could use this recursion to sort of use these guys having the statement be true and implying the next one is true. We'll show an example of doing that, not with the Fibonacci numbers, but with another one. So I carefully cooked up an example because when you do recurrences, a lot of times things don't work out that nicely. Like the Fibonacci recurrence it's very simple, that the next one is the sum of the previous 2. But the formula for the Fibonacci recurrence is hairy with all sorts of square roots of 5s in it. It's a little bit ugly unless you manage to, well, you can compartmentalize that a little bit and call never mind. I'm going to drop it. But I've cooked up one where all the terms in the formula we're going to need are integers, so we have nice whole numbers to work with. Okay, so the sequence then is a little bit like the Fibonacci sequence, but or the recursion is a little bit like that one, but slightly different. To get the next one, you add the previous one and twice the one before it. Okay. So I skipped 2 slides, but anyway, yeah, I just said that, and I wanted to write that in words. The next number is the sum of the previous and twice the one before that. Okay. And then here's some initial values. X sub 0 is 2, and x sub 1 is 1. And that's what we need to kind of get things started, because the smallest one of these statements that makes sense, I guess, would be when n was 2, in which case n minus 1 would be 1, and n minus 2 would be 0, and we would need precisely these two values. So can you quickly figure out what would be the value of x2? Xn minus 1 would be this 1, and xn minus 2 would be this 2. So we're looking at 1 plus 2 times 2, which is 5. Well, there's the first couple of values, 5, 7, 17. I think it might be smart for me to do a few of those on the calculator. All right, so let's see. We know that we've got 1 and 2. So the first one I did was 1 plus 2 times 2. That was the 5. The next one then would be, to get that 7, that's x sub 3, I would be looking at the previous one, which is this 5, okay? So we can hit second answer, plus 2 times the one before that, which is a 1. Okay, that's how I got the 7. Now, the only thing I'll need to do is change that number. I want the previous answer plus 2 times the one before that, and that won't be 1 anymore. It'll be 5. That's where our 17 came from. I'm going to try that one more time. So, whoops, not the wrong thing. Second entry. This, if I do this with the 5 replaced by 7, I should get the next number in the sequence. Well, wait, you guys don't know what the next number in the sequence is yet. I only, on the slide, only gave us up to this 17, but I guess x sub 5 would be 31. And, well, it turns out there's a fairly easy formula for this sequence of numbers, and it is this. It's 2 raised to the n power plus or minus 1. And it's minus 1 when n is odd, and it's plus 1 when n is even. See that if you put minus 1 to an even power, you'll get a plus 1 here. And if you have a minus 1 to an odd power, you'll be subtracting 1. So, wow, that wasn't obvious. But maybe looking at these numbers now, you can see it. See how 5 is 1 bigger than 4, and 7 is 1 less than 8. 17 is 1 more than 16, and 31 is 1 less than 32. Okay. So here's a stating that what we just discovered is I don't know if we discovered it, but once we saw the pattern, we recognized a pattern. But it's a true thing. For all n, if n is greater than or equal to 3, x sub n, as previously defined by a recursion, can be done in one fell swoop. It's 2 to the n plus minus 1 to the n. So, if I had to go through this stuff to get out to the 15th number in the sequence, I could do it. I would be unhappy about it, but I can do 2 to the 15. 15's odd, so it'll be minus 1. I can get an answer right away from the formula. See how a formula is really a nicer thing to have than a recursion. Well, I suppose it's nice to have both of them, but a formula is handy. We had a similar thing happen when we talked about binomial coefficients. There was a way to recursively write down the next row of Pascal's triangle if we knew the previous one. But, when we got a formula for the binomial coefficients, remember the thing with the factorials in it, and the fraction? Yeah. it became a little bit quicker, a little bit easier. We could figure out 52 choose 5 without having to write 51 other rows of Pascal's triangle first. So yeah, having a explicit formula for a sequence, the terms of a sequence, is definitely kinder than having just a recursion. Okay, so we're going to prove that using complete induction. This issue I had before about the base cases is present here, and it's making me unhappy. The problem in our proof is that we're going to be using the recursion in it, which is valid for n from 3 upward. Yeah? But the formula that we're trying to prove is correct is actually valid for n from 0 upward. It works at n equals 0. Yeah, so I don't know, there's a mismatch. So this is one of these cases where I'm just like, be stupid about it and fill in the base case. Okay, yeah, so this is what I just said with my voice, but I didn't open the slide to the right spot. When n is 3, the recursion for xn refers to values that are not covered by the theorem. But notice that x sub 0 is 2, and that's also equal to 2 to the 0 plus minus 1 to the 0. But that's 1 plus 1, isn't it? You do that calculation. 1 and 1 is 2. Additionally, note that x sub 1 is 1, and that is also equal to, look at our formula when we stick a 1 into it, where the exponent is. 2 to the 1 plus minus 1 to the 1. So it's 2 minus 1. Yeah, that's 1. I can't really call those the base cases for this theorem we're trying to prove, because the smallest value in the sequence of statements is n equals 3, or 2. Yeah. Wait, I think I've got this mislabeled. x0, x1. Yeah, that should be n equals 2. Excuse me. Well, I just went back and corrected that in the slide, so it looks right now. Highlighting on one. N equals 2 is the earliest stage in the complete induction thing. But when I did that, when I went to look at the source code for my slides, I realized that I had the same error back here in the theorem. So let me point that out to you too. This is true from n equals 2 onward, that this formula works. And in truth, because we just, in this not quite the base case part here, verified that it also works at 0 and 1, you actually have a bigger result that the formula works from n equals 0 to infinity. Okay, so what are we doing? So I didn't fix that 3. But anyway, suppose k greater than or equal to 2 is an integer such that for all j less than k, we have xj is, well, the formula works, right? So what are we going to do? In particular, we're going to notice that the k minus first value of this sequence is going to have this power, this power of 2 and of minus 1 formula be its value. And similarly, the formula works when we're at the k minus 2 stage. Okay. Then, and here goes a big pile of algebra. Since you know that xk is the sum of the previous one and twice the one before that, so just write the given recurrence. And then you know the inductive hypothesis applies for both of those, so each of them can be re-expressed as a thing that looks like power of 2 and power of minus 1 with the same power as the index on the thing. So this, I'm replacing x sub k minus 1 with this whole formula. Notice how the powers there are the same as the subscript there. And then we're doing the same thing with x sub k minus 2. And that's the one that from the recursion has a factor of 2 applied to it. But this part inside the parenthesis is just the inductive hypothesis at stage k minus 2. So we didn't need all of the statements prior to be true. Really, it was just the last two, the k minus 1 one and the k minus 2 one. So then what did we do next? Just regrouped. I just took the 2 times 2 to the k minus 2 and put it together with this other thing that's a power of 2. In fact, that's a succinct way to say what the regrouping is. I put the powers of 2 together, and I put the powers of -1 together. Then notice that I think the only thing I did on the left anyway is multiply in 2 times 2 to the k minus 2. That's a 2 to the 1 times a 2 to the k minus 2, and so the exponent bumps up by 1, and we get 2 to the k minus 1. Did I do anything on the right? I think I did too. Notice how both of them have the k minus second power of -1 in them. So I can pull that much out, and I'll be left with a -1, and then just this -1 to the 1, right? And then this 2. Okay. Little bit, not much of a step here. Well, actually, two not much of a steps here. 2 to the k minus 1 plus 2 to the k minus 1. That's 2 times 2 to the k minus 1. So, of course, that's 2 to the k. Doesn't highlight the k properly. All right. And then I just added 2 and -1 and got 1. Woohoo. Then, because this is a step that I think people wouldn't think of, I wanted to break this out so you see it. 1 is the same thing as -1 squared. We know that. But why would I want to replace 1 with -1 squared? Because then I have, on the right side of this sum, I have -1 to a power and -1 to another power. And when you have something like that, you add the powers. K minus 2 plus 2 gives you k. And that's great because that's what we were trying to get to, that the formula for x sub k, in terms of power of 2 and a power of -1, that whole thing works at stage k. So that was the desired ending point. Great. Well, that's QED for that sucker. Let me do one last example of a type of problem that you can use strong induction on. Although my advice in the end on this type of problem is to not use strong induction, but it could be done with strong induction. So this is a category of problems we've actually saw in one of the group activities earlier. This type of thing, a postage stamp problem. Basically, there's also a version that, if you've seen the movie Die Hard with a Vengeance, I think it's called. There's a Bruce Willis movie where like a building is going to explode unless he solves a math problem, which is like my dream come true. I'd be like, oh, great, I could get this. But Bruce Willis manages to do this thing where he's supposed to measure out exactly, I forget what maybe it's 4 gallons of gas using 2 containers that have capacities of 3 gallons and 5 gallons. Or, it's a variant of that. But the gas version of this would allow you to both add and subtract numbers. But with a postage stamp problem, you can only put a stamp on, you can't take one away. So postage stamps problems are about positive linear combinations of 2 values. Anyway, I think it's fairly clear to most people what's going on. If you have a couple of different stamps that you can use, a couple of different denominations of stamps you can use, not every possible postage can be achieved. Like if I only have 3-cent stamps and 10-cent stamps, well, I can't get 1 cent or 2 cents worth of postage. Of course, there's very few places that would deliver a letter with only 1 cent worth of postage on it. But anyway, there's holes early on, but eventually you can usually get every postage, every possible postage. What you need is what's called a necessary condition here, is that the two, if it's only 2 types of stamps, they have to be relatively prime to one another. They have to have no factors in common. Because if they did have factors in common, the postage you're going to get will always just be a multiple of that common factor. So you're not going to cover every possibility. Think about what would happen if you had, say, 3-cent stamps and 9-cent stamps. You'd never be able to get away from a multiple of 3. So in that case, you'd have holes all the way down the line. But if you have relatively prime stamp values, then you can have some early holes, but then eventually start getting everybody. I just said that. Okay, so let's look at the case where we have 3-cent and 5-cent stamps. These are the values you can get. Of course, you can not put any stamps on and you'll get 0. And you can, the smallest positive postage you can get is from putting 1 3-cent stamp down. So you can get 3. And then you, of course, can get 5. But you can't get 1 or 2 or 4. Right? Those are some of the early holes. You can get 6. Oh, yeah, that's 3 and 3. Can't get 7. I don't know. Can you get 7 with only 5s and 3s? Well, you can sort of argue exhaustively here. The small things are either 2 3s, 2 5s, or a 5 and a 3. And those get you respectively 6, 8, and 10. Well, I think I said them in the wrong order, 6, 10, and 8. But yeah, the reason I got confused for a second is I ran into 9 and thought, oh, wait, we can't do that. But then, yeah, we can. So my brain was spinning there internally for a minute. That's 3 3-cent stamps, yeah. So do you notice we've got 8, 9, and 10? Can you really do 11? Well, we should start thinking inductively. If I wanted to know that I could do 11 by knowing that I could do some earlier values, what would be a smart way to do that? Well, for instance, I could look all the way back to here and say, oh, I can do 6, and 6 plus 5 gets me 11. But I could be maybe a little bit smoother than that and say I can do 8 already, and if I just add a 3-cent stamp to that, doesn't that get me an 11? So we're starting to think about using previous values to get us the truth of a sentence at later values, but they're not the one right previous, they're the one several back that we need to use. This is a true sentence, but I wonder if it makes sense to everybody. As soon as you have 3 consecutive achievable postages, you get everything. So, in fact, our first 3 consecutive achievable postages are right there, 8, 9, and 10. And why does that mean we get everything? Well, think about adding 3-cent stamps. From 8, you can get 11, and then 14, and then keep going down the line by adding more and more 3s. From 9, you can get 9, and then 12, and then 15, and so on there. And 10 gets you 10, and 13, and more that way. So as soon as you have 3 in a row, you end up getting everything. And why is it why is it 3 in a row that's important? Well, it's because we have 3-cent stamps. Yeah, there you go. I said it. We can add some number of 3-cent stamps to one of those to get any larger value. So that's a theorem. Any postage greater than 7 cents can be achieved exactly using only 3-cent and 5-cent stamps. So this is an argument that can be completed using complete induction, but it suffers from this issue about the base case, and I think it's more confusing done that way, to be honest. So even though we're here in the section on complete induction, my recommendation is that you don't. If you haven't run into IMHO, that's in my humble opinion. Anyway, a simpler approach is to combine ordinary induction, and it'll be induction on K now, with these 3 exhaustive cases. If X is 8 or larger, it can be written in the form 3K plus 8, or 3K plus 9, or 3K plus 10. And those correspond to the 3 possible values mod 3. This is 2 mod 3, this is 0 mod 3, and this is what's left, 1 mod 3. Okay. So I think I'm going to weasel out of doing that, but again, that's a great exercise for a student to try. Write a kind of a 3 parallel induction arguments, or you can think of it as 1 with cases inside of it. So my anal retentiveness or obsessive compulsive disorder came to the fore, and I really had to fix it. I don't know if you noticed that the spacing was weird after the sense symbol in this, but I fixed that because I had to. And the other thing I wanted to finish up was I have a lingering sense of guilt about showing you this really cooked up example of a proof using complete induction for a recurrence relation. And it seemed a little unfair because the stuff works out with nothing but integer arithmetic. So I thought I would show you how that plays out with something a little bit tougher, the Fibonacci recurrence. There it is. That is the actual formula for Fibonacci numbers. And I think for most people, they look at it and go, ooh, not pretty. But it's actually kind of nice if you see certain things inside of it. So to help with that, I actually started up a Sage worksheet. And that number that appears, well, it appears right here, 1 plus root 5 over 2. That's got that's got some special significance. That is its decimal value, 1.618, and lots more. It's an irrational number, I think, pretty obviously. It's famous as, it's called the golden ratio. And so that the golden ratio pops up in terms of a formula for the Fibonacci numbers, that's odd. The other number, I'm calling it B here, is also related to the golden ratio. It's its negative reciprocal. Okay, we're gonna need to first prove a little lemma, and we can go on and finish the proof by complete induction of the formula for the Fibonacci numbers, which is the point here. So the lemma I want is that alpha and beta both satisfy a certain polynomial type relation. They satisfy this relationship, and in fact, this effectively is the Fibonacci relationship that I'm about to write down. Now that's the Fibonacci relationship, except in Fibonacci these were subscripts, and here they're superscripts. So these really do mean, x to powers, but you notice it's the same numbers. The nth one is equal to the sum of the n minus first and the n minus second, of course, in terms of powers. So let's prove that, and it turns out to be really easy. If you have this relationship is true, if you have x to the n is equal to x to the n minus 1 plus x to the n minus 2, notice that you can factor out an x to the n minus 2. Let me just first copy it, because I feel bad about writing equals to something that's above the proof line. So suppose x to the n is equal to x to the n minus 1 plus x to the n minus 2. We'll just factor out an x to the n minus 2, and you have, well, maybe I shouldn't say factor it out. Divide both sides by it, and then cast it aside, or see what's left. That's me. You get x squared is equal to x plus 1. And by dividing by x to the n minus 2, we actually just threw an assumption in here that x is not equal to 0. Because otherwise we'd have been dividing by 0, which would be disallowed. So if you know that, or if you think you have a thing that has this polynomial relationship, x to the n equals x to the n minus 1 plus x to the n minus 2, it'll also satisfy this. A number that satisfies the above will satisfy this. And vice versa, if you've got a number that satisfies this quadratic, it's going to satisfy that one too, provided it's not 0. 0 isn't a solution to the quadratic, so that isn't really much of an issue. Great. So what's the solution to the quadratic? Well, this is, if you put everything to one side, you find that you've got the coefficients are 1, minus 1, and c is also minus 1. So you can just plug that into the quadratic formula. So the x is equal to negative of b plus 1, plus or minus the square root of b squared, minus 1 squared is 1, plus 4, or excuse me, minus 4ac. I'll just write that down for now. Minus 4 times 1 times minus 1. All divided by twice a, which is a is 1, so that's a 2 in the bottom. And, well, doesn't take much to see. That's root 5. Because of the two minuses, this is really 1 plus 4. And we've got 1 plus or minus root 5 over 2. And one of those is alpha, and when that's a plus sign, and the other is beta when it's a minus sign. Now, this is actually reversible too. If alpha and beta are roots of a polynomial, then up to a constant, it's this polynomial. You could multiply, you could scale everything by a fixed number, but that wouldn't really change the solutions, the roots. But up to a constant, this is the polynomial, and if this polynomial is true for those numbers, then this higher powered thing is true for them, because we know neither of them is 0. So, yeah, alpha and beta do both satisfy this funky relationship. We're going to use that when we do a PCI proof of the Fibonacci, the formula for the Fibonacci series. So, the theorem we have to prove is this. For all n in the naturals, f sub n can be written as 1 over root 5 times alpha to the n minus 1 over root 5 times beta to the n. Now, what I'm going to do is not prove this for all n, but rather prove it for n2 and greater. So for all n, let's just say this upstairs, n greater or equal to 2. It's also true when n is 1 and when n is 0, though. So let's just note that. Not so much a, well, I guess I should think of this as a base case. Yeah, let's say it as a base case. In which case, forget that. We'll leave that out. Just do it for all n. So think of this as me being extra careful, but really this is funny because you do indeed need these to be true before the complete induction works. In fact, we need two things, a course of values to be true. When n is 0, the formula is really easy because you get 1 over root 5 times 1 minus 1 over root 5 times 1. That's well, let's write it as alpha to the 0. And beta to the 0, but that's 0. And we also know that the 0th Fibonacci number is 0. At least the way I number them. Some people start with the 0th one being 1, but let's stick with this for now. We also need to look at n equals 1. Because the recurrence doesn't really, I'm pointing at the wrong thing, the recurrence for Fibonacci numbers doesn't really take hold until you've got these two values down, and then you begin able to use the recurrence. Okay, so figure out what the formula would give us. We have 1 over root 5 alpha to the 1 power minus 1 over root 5 beta to the 1 power. I'm going to stretch that across the bottom of the screen here. That is, remembering what alpha and beta were, that's what alpha is, and then minus 1 over root 5 times beta was the same except with a subtraction in the middle. 1 minus root 5 over 2. I'm going to start at the top of the screen now and come down. Well, this is, we might as well just distribute everything and figure out what we're looking at. The denominators are all going to be 2 times root 5. So that's a big fraction with 2 times root 5 in it. The numerators are going to be 1 plus root 5, plus another 1 and a minus root 5. No, I think I messed up. The signs on these are off. This was, both of them positive, but this one we're subtracting a plus 1 and it's subtracting a minus 1. Yeah. So this should have been a minus and then a plus. Right, so what happens? You get 1 and minus 1 and they knock each other out. And root 5 plus root 5, but over 2 root 5. Yeah, this is equal to 1. And what's the other thing? F sub 1 is also equal to 1. So depending on how you want to think about it, we've either accomplished the base case or sort of the initial part of the inductive step that's not handled by the recurrence. In any case, let's move on and do the inductive step for real. And you'll see while we're in the midst of that where that lemma I was interested in comes up. All right, so we're going to assume we've got some value k down the line, a Fibonacci number fairly far down the sequence. That's a k greater than or equal to 2, so that we know that the recursion applies for that k. What I'm going to do then is just say what f sub k is equal to. It's equal to the sum of the previous two guys, right? So it's equal to f sub k minus 1 plus f sub k minus 2. And that's just the Fibonacci recurrence, which all the elements of the Fibonacci sequence satisfy. But these guys satisfy something else because they're smaller than k. So by the inductive hypothesis, we get to write those things in terms of that formula with powers of alpha and beta. So this first one is 1 over root 5 alpha to the k minus 1 minus 1 over root 5 beta to the k minus 1. Let's parenthesize that. So the thing in parentheses is our f sub k minus 1. And then we'll have also the same thing, but with k minus 2's in it. And then let's just regroup so that things involving the same variable are together. We'll put the two alpha things together, the two beta things together. That's just going to be algebra. Let's look at the top of the screen and head downward again. All right, so that's equal to, putting the two things with alpha together, you get, and both of them have a root 5 in it, so I'm going to pull that out. We have alpha to the k minus 1 plus alpha to the k minus 2 remaining. Yeah, and then the things involving beta, notice both of them have a minus sign on them, because this is addition in between, so there's no funny business here. Minus 1 over root 5, and now some minus 1 over root 5. We can pull that minus 1 over root 5 part out, and what remains is same powers on beta that were on alpha. So yeah, these two things are a sum involving consecutive powers of alpha, and so that means the next power of alpha is equal to the sum of those two. And very similarly for the beta, because those are the two solutions to that quadratic formula we looked at before. So we've got alpha to the k minus 1 over root 5 beta to the k. And that is our QED moment. Okay, so that was fun. And now I'm just back to this to sign off and say, try to read chapter 6.1, section 6.1, and really thanks now for sticking it out to the end. Have a great rest of your day.